Bismillahirrahmanirrahim. Assalamu alaikum dear students. Today is the 20th lecture of Discrete Structures CSC 102. In the previous lecture we have started functions. We have studied and discussed some basic notions and definitions of functions. What is a function? Function is basically a relation which satisfies two additional conditions. We have studied also, we have seen some examples of functions, and we have also discussed some conditions under which the function is not well defined. Today we are going to continue our lecture of functions. Today we shall talk about one-to-one function, onto functions, bijective functions, or it is called one-to-one correspondence, and inverse functions. First of all, I shall discuss what is basically the sum and difference of two functions. For adding two functions or subtracting two functions, the functions must be defined on the same sets. This is the first thing. F and g, if we have two functions, f from R to R, g from R to R. R is basically the usual set of real numbers. Now f and g, to take the sum or difference of these two functions, the first thing is that these two functions must be defined on the same sets. Now we can define sum of f plus g, f and g, or difference f minus g. If we define sum, we write f plus g. If we define difference, we write f minus g. Here also minus, here also minus. So we define a new function f plus g, which is defined on x, f plus g of x. This is basically the sum of f of x plus g of x. This is how we take the sum of two functions. For example, if we have f of x is equal to 2x plus 3, this function is defined on the set of real numbers, and another function g of x, which is maybe x minus 1. Then f plus g of x, this is basically the sum of two functions, which is defined as f of x plus g of x, means 2x plus 3 plus x minus 1. So this is 3x plus 2. So this is the sum of these two functions f and g. Similarly, we can define the difference of these two functions. Now we discuss another property of functions, which is basically the equality of functions, when two functions will be equal. For this we have a theorem which shows the equality, which shows the conditions of the equality of two functions. If we have two functions, f from x to y, g from x to y, to show the equality, the first thing is that both functions are defined on the same sets. F is defined from x to y and g is from x to y. If they are defined on different sets, we cannot show them equal functions. For two functions can be or may be equal, the first thing is that their domain and ranges or codomains is same. Then we move further. Then f is equal to g. We say that the function f is equal to the function g if and only if f of x is equal to g of x for all x belongs to the domain set x. Means images of these functions at every x must be same. Images we have discussed in the previous lecture. What is the image, pre-image, inverse of the function. To understand better the equality of functions, we consider a simple example. which is in this example the function f and g are basically the Boolean functions defined on the set J3. J3 is 0, 1, 2. This is a set J3, and define two functions from f and g from J3 to J3. Means f is basically a function. F is basically the function f from J3 to J3, and g is the function from J3 to J3. So the first thing is to check whether the two functions are defined on the same sets. Yes. Now we go further. We will try to find the images of both functions, and we'll see that whether the images for all x belongs to x are same or not. F is defined like this: f of x is equal to x square plus x plus 1 mod 3, and g of x is x plus 2 whole square mod 3. So does f of f is equal to g or not? Now we have to check whether the images f of x and g of x are all same for J3 or not. That is, we have to check f of 0 must be equal to g of 0, f of 1 must be equal to g of 1, f of 2 must be equal to g of 2. So this is we have to check for all the elements of J3. So first we have to calculate these functions. We take here x as 0, 1, 2. We simplify x square plus x plus 1. If we take 0, here 0, 0, 1. If we take 1, 1, 1, 1, 3, 2, 4, and 2, 6, and 1, 7. So this is this. Next we calculate this, x plus 2 whole square. 0 if we take, here we have 4. If we take 1, here we get 9. If we take 2, here we get 2 plus 2, 4. 4 square is 16. Now we can calculate f of x. F of x is basically x square plus x plus 3 mod 3. So here we have to check for, if we take x1, f of 1 is basically 1 square plus 1 plus 1. This is, so if we take 0, sorry, so then f of 0 is basically here this is 1, this is 1 mod 3. So 1 mod 3 is basically 1, as if we divide 1 by 3, the remainder is 1, because 3 can be written as 0. 3 can be written as 0 into some integer, whatever it is, 1 plus 1. So when we divide 1 by 3, the remainder remains 1. So this is the remainder. So 1 mod 3 is 1. Similarly, we can calculate 3 mod 3, which is 0, because when we divide 3 by 3, the remainder is 0, because it is a mod function. You know what is the mod function? We have studied it in relations. The next is 7 mod 3. This is when we divide 7 by 3, the remainder is 1, because 3 2s are 6, and 7 minus 6 is 1. Similarly, we calculate this. 4 mod 3 is 1, because when 4 is divided by 3, the remainder is 1. When 9 is divided by 3, the remainder is 0. When 16 is divided by 3, the remainder is 3 5s are 15, and 16 minus 15 is 1. Now we check for all values of J3, means 0, 1, 2. F of 0 is what? 1. G of 0 is 1. F of 1 is 0. G of 0 is 0. G of 0 is 0. F of 2 is 1. G of 2 is also 1. Now we can check 1 is equal to 1, means f of 0 is equal to g of 0. We can check here f of 1 is equal to g of 1, here we must write 1, and f of 2 is g of 2. Therefore we can say that for all x belongs to J3, we have f of x equal to g of x. Therefore we can say that f is equal to g, means both these functions are equal, as the images of these functions are equal for all possible values of x in J3. So I hope you understand how to check the equality of two functions. Two functions are equal whenever their images f of x is equal to g of x for all x belongs to the domain set x. So now we move to the one-to-one functions. One-to-one functions, in short, if we look at the arrow diagram here at this which we have studied in relations, if one element of the domain is related to one element in the range for all elements, if here you can see that 1 is related to one element, this 2 is related to only one element, 3 is related to only one element, 4 is related to one element, 5 is related to only one element, or you can say that 5 is related to only one element, 6 is related to only one element, 7 is related to only one, 8 is and 9 is also related to only one element. If in the arrow diagram of the functions one element is related to only one element, we have only one arrow with each element, then such type of function is basically a one-to-one function. One-to-one, as by name, this is basically one-to-one, means here we have one element, here we have one element, so this is one-to-one. So such type of functions are basically called one-to-one functions. And now we can read the proper definition of the one-to-one functions. Let f be a function from a set x to a set y. If we have f is basically the function from set x, this is set x, this is set y, and f is basically the function from x to y. F is one-to-one, or we say it injective. F is called one-to-one function, or f is called injective function if and only for all elements x1 and x2 in x. If we take two elements, here x1 is here, x2 is here, in x, x1 and x2 are basically the elements of the domain set. If we have f of x1 is here and f of x2 is here in this set, if the images of x1 and x2 are equal, if both these are equal, if images f of x1 and x2 are equal, then the pre-images must be equal. You can say if the images of x1 and x2 are equal, then x1 and x2 are equal. What does it mean and how we can interpret this definition? For example, here means that if image is 1, f of x1, f of x2 are equal, what does it mean? If we have, for example, f of x1 is this, and f of x1 is 6, f of x2 is also 6, what does it mean? They are equal. Then the pre-images are also equal, means x1 is equal to x2, because 6 is image of what? 2. This is x1, and here the 6 is image of what? 2. Here we have x2 is also the 2, means 2 is equal to 2. Here 2 is equal to 2. What does it mean? If you think and concentrate on this definition, it means that for an image, for an element in the set y, for example, x is this and y is this, for an element, for one element of y, there is only one element in x, means for an image there is only one pre-image. This is what this statement says. Means if the image is 1, then pre-image is 1. If the element of y is 1, then the element of x is 1. This is what this statement says. Or equivalently, the converse or inverse, whatever you can say that. Equivalently, in this definition, first we check the image. If there is one image, then the pre-image is 1. This is how we can interpret it. Now, if we say that if x1 is not equal to x2, then f of x1 is not equal to x2. These two statements are logically equivalent. This is basically, you can say, contrapositive. This is the contraposition of this statement. As you know, P implication Q, we have a conditional statement. The contrapositive is not Q implication not P, if I am right. So these two statements are logically equivalent. So either we check this or we check this. So if in the second statement, if x1 is not equal to x2, means if there are two different elements of the domain, then their images are also different. This is what here, if we take x1 equal to 2, x2 is equal to 3, then x1 is, for example, 2, x2 is 3, then x1 is not equal to x2, then their images f of x1 is not equal to f of x2, because f of x1 is what, 6, and f of x2 is 7. They are also not equal. This is basically the equivalent form of that statement which we have seen here. Either of these two statements, whatever you prove, you will prove that the function is 1 to 1. Symbolically, f is from x to y is 1 to 1 if and only if for all x1 x2 belongs to x, if f of x is equal to f of x2, then f x1 is equal to x2. This is the first statement you can see. So this is basically the proper definition of the one-to-one functions. Next we are going to discuss one-to-one functions with the help of examples, so that you can get the basic idea what is basically the one-to-one function and how we can recognize and prove the functions to be one-to-one. For example, we are given here two arrow diagrams of the functions. The first is this and the second is this, and we have to identify which arrow diagram represents a one-to-one function and which is not a one-to-one function. For example, this is a function f a b c d. It is the domain of this function, and the codomain is u v w x y. The image of a is w, image of b is v, image of c is x, image of d is y. Whether this satisfy the condition of the one-to-one function or not. Every element in x and every element, or not every element, and elements in y, basically each element in y, or you can say that an element in y is related to exactly one element in x. Means if f of x1 is equal to f of x2, implies x1 is equal to x2. If this condition is satisfied in this arrow diagram, if we take one element in y, its pre-image is only 1. For all elements it is true. Yes, it is true. So this function is a one-to-one function. Now in this second arrow diagram, you can see that if we take f of x1 is equal to f of x2, for example, this is w and this is w. Now the pre-image of w is what? W the pre-image of W is A and pre-image of W is C. Whether are these two numbers are equal? No, because A is different, C is different. Now you can imagine this condition here in the better sense, that if range is one number, its pre-images are 2, because if we take W is equal to W, but its pre-images are A and C. Now A and C are not equal, so this condition is violated here. This condition is true here, but here in the second case it is violated. Therefore this arrow diagram doesn't represent a one-to-one function. Or alternatively, as we have seen the second statement here, we can define this condition equivalently as this. We can verify this also in this case. If we take here A is different from C, does this imply f of A is different from f of C? No, because A is different from C, but f of A, which is W, this is equal to f of C. So this condition is violated here in the second arrow diagram. Therefore this arrow diagram doesn't represent a one-to-one function. So I hope you understand the basic idea behind the one-to-one functions. So now we move to the one-to-one functions on infinite sets. The previous example involved only the finite sets. Now we are going to discuss an infinite example in which we shall show that the function is one-to-one or not. So these are the same conditions which we have discussed in the previous slides, that to check a function whether it is one-to-one, we have to check for all x1 and x2. If f of x1 is equal to f of x2, then x1 must be equal to x2. So how to prove two infinite functions to be one-to-one? First, we suppose that x1 and x2 are any two arbitrary element of capital X, which is domain of the function. We suppose that f of x1 is equal to f of x2, and then we show that x1 is equal to x2 by using some mathematical identities and results. And to show that f of x is not one-to-one, we take f of x1 is equal to f of x2, and we show that x1 is not equal to x2, or we find some counter example to show it. Usually we find counter examples to show that this function is not one-to-one. Now an example of the functions which are defined on infinite sets. The first example is this function. F of x is defined as f of x equal to 4x minus 1, where f is a function from R to R, where R is the set of real numbers and G is the set. G is basically a function which is defined from Z to Z, where Z is the set of integers. F of x is defined by this, and G of n, because here we cannot write x, because we can write, but here the usual notation for integers is n and usual notation for real numbers is x. So here we define G of n is equal to n square. So this is for all n belongs to Z, and this is for all x belongs to R. Now we have to prove or disprove whether f is one-to-one, whether G is one-to-one or not. If we are not succeeded to prove that f is not one-to-one, then we shall try to give a counter example that it is not one-to-one function. First we take the function f and we try to prove it that it is a one-to-one function. Sorry. This function is defined like this, 4x minus 1, and how we proceed we have discussed it on a previous slide here. How to proceed, how to prove a general method of we adopt the usual method of direct proof to prove it. We suppose that there are two elements x1 and x2 such that their images are equal, and we try to prove their pre-images are equal. Or equivalently, we can prove it by using the other definition. We suppose x1 is not equal to x2, and we prove that f of x1 is not equal, and we prove f of x1 is not equal to f of x2. So this is an alternative technique to prove whether the given function is one-to-one or not. So we will discuss both techniques, but first is this. We suppose that x1 and x2 are arbitrary two real numbers, and we suppose that their images f of x1 is equal to f of x2, and we must show that x1 is equal to x2. If f of x1 is equal to f of x2, then f of x is equal to this. F of x1 will be 4x1 minus 1, and this is equal to 4x2 minus 1. So adding both on both sides, if we add both on both sides, 1 will be cancelled out, and we are left with 4x1 here is equal to 4x2. Now dividing on both sides by 4, this 4 cancels with this, and we get x1 is equal to x2, which is what we had to show. So we started with this by supposing images are equal, and we have proved that pre-images are equal. So we have proved that this function is one-to-one function. We can use the alternative technique. For example, if we suppose x1 is not equal to x2, this implies 4x1 is not equal to 4x2, and this implies 4x1 minus 1 is not equal to 4x2 minus 1, and this implies f of x1 is not equal to f of x2. Here we have used the alternative technique, in which we suppose that x1 is not equal to x2, and we have arrived at f of x1 is not equal to f of x2. So therefore this function is one-to-one. We have proved it by using two alternative techniques. The first is by supposing images are equal. We have proved pre-images are equal, and then the second technique is by supposing the pre-images are different, are not equal. We have proved the images are also not equal. So you can use both these techniques depending on the situation, whichever is easy. So this is how we can prove functions to be one-to-one, which are defined on infinite sets. Now we come to the second function, which is defined on z set of integers, g from z to z, and is defined by the rule g of n is equal to n square for all n belongs to z. Then g is not one-to-one. Why? Because we cannot prove that. We cannot prove this, and we cannot prove this. For example, the counter example of this, if we take two different elements, for example n1 is not equal to n2, and we take it 2 and this as minus 2. But if we take g of n1, this is what? This is 2 square, and if we take g of n2, this is basically what? Minus 2 square, and this is 4. This is also 4. Then we can see that g of n1 is equal to g of n2. So this is basically we started at n1 is not equal to n2, and we are arrived at g of n1 is equal to n2. So this violates this condition, the second statement which we have studied. So this function is not a one-to-one function by the definition of one-to-one functions. Similarly, we can reverse the order of calculations and we can prove it by the other technique. So this function g, which is from z to z, is not a one-to-one function. Now we move to the on-to functions. First we shall discuss it on the finite sets, and then we shall discuss these type of functions on infinite sets. Let f be a function from a set x to a set y. Similarly, as we have defined, f is a function from x to y. F is called onto function, or f is called surjective function. Onto functions are usually called are also called surjective functions, and any function f is onto if and only if, given any element y in y, it is possible to find an element x in x with the property this. Symbolically, we represent it: f is from x to y is onto if and only if for all y belongs to y, there exists some x such that f of x equal to y. Now, what does this expression or this statement means? It means that every element of y, every element of the second set, which is codomain set, which is this, the codomain set, every element of the codomain set must have some preimage. Every element of y must have some preimage. Means for every element in y there exists some x such that the image of x is y. So means every element of y must be utilized. You can say that no element of y should be extra or without any preimage. So this is kind of functions which is called onto functions. For example, here if we have this set and if we have this set, now this codomain set y basically have 4 elements: 1, 2, 3, 4. Now every element have some preimages, this. So such type of functions in which every element of codomain have some preimage. If there is some element, for example, in this arrow diagram, domain has 3 elements, range has, your codomain has 1, 2, 3, 4, 5 elements. Now here first element has preimage this element has this preimage, this element has this preimage, but there is this element and this element. These two elements don't have preimage, don't have preimage. Or you can say that there exist some elements in the codomain set who don't have preimage, who are not related with the elements of x. So such functions are not onto functions. So we see it with the help of example, which in these two arrow diagrams we have to identify which one is onto function and which one is not onto function. So in the first arrow diagram you can see 1 is related to A, 2 is related to C, 3 is related to C, 4 is related to D, 5 is related to D. Now there is one element in Y, this. B is not related or be related to any element in X, or B doesn't have preimage, B doesn't have pre-image. There exists some element y in y for which we cannot find any element in x, such that f of x is equal to that b element. So therefore this arrow diagram, the first arrow diagram, this is not onto function, not onto function, this one. Now we look at the second arrow diagram. One is related to B, 2 is related to C, 3 is related to A, 4 is related to C, 5 is related to D. So every element in Y is related to some element in X. We can find for all elements in Y, we can find some element in X such that f of x is equal to y, or here we have defined g, so here we must have g of x is equal to y. So this condition of onto function is satisfied here, therefore this function is onto function. One thing sorry, one thing we can say about the onto functions, that if range of the function is equal to the codomain of that function, then that function will be onto. We can say this because if we look at this diagram or the definition of onto function, if range of any function, f, whatever it is defined here, if range of that function is equal to the codomain of that function, then that function f is onto function. What is this? Basically, range of that function contains only those elements which are images of some elements of x. If range and codomain become identical, then we say that this function is onto function. Now we have discussed onto functions on finite sets. Now we shall discuss onto functions for the infinite sets. How to prove a function on an infinite set to be onto function or not. Now suppose f is a function from x to y, and suppose y is infinite by definition, and second set is infinite. Then how we prove it onto function? By definition, f is onto if and only if the following universal statement is true: for all y belongs to y, there exists some small x belongs to capital X, such that f of x is equal to y. Thus, to prove f is onto, you will ordinarily use the method of generalizing from the generic particular. We suppose that y is any element of y. Y could be any element of y, and we show that there exists some element x in x with such that y is image of that x. So we have to show it, and to prove any function is not onto, we find, or we give a counterexample in which we shall try to find an element y of y such that there is no x whose image is y. So this is how we prove any infinite function, or a function which is defined on infinite set, that it is onto or not onto. Let's take the same example. Same example. No, this different example. The first part is same as we have used in one-to-one function, but the second is different. I'm giving you some particular examples which are easy to understand here in the lecture, but in the book of Discrete Mathematics, Susanna and Rosen, I have recommended you can see, you can find many other examples of functions which can be proved one-to-one and on-to, and for your practice you can try them. Now we have two functions, f from r to r and h from z to z. Once again, r is a set of real numbers, z is a set of integers. By the rules, we define f like this, and g h of n is equal to 4n minus 1. Now we have to prove or disprove whether f and a function h are onto or not. If they are not, we have to give a counter example. So how to prove? I repeat here, for all y belongs to y, we shall prove that there exists some x in x such that y is image of x under the function f. Now in this particular type of functions, which is f from r to r, for all elements y which are in r, we have to prove that there exists some x in this set belongs to r, such that if we take up the image of x under f, that is f of x, this is equal to y, means this is equal to y. So we have to prove this. So first of all, we suppose that y is any element of r, and then we shall try to seek, or we shall try to find some x belongs to r such that f of x is equal to y, means f sends x to y. First we shall prove that there exists real number x such that this, and then we shall prove that does really this function f sends x to y or not. So there are two steps to prove functions to be onto. So first we say that let y is any arbitrary element of r, and we must show this, now y is equal to r, y belongs to r, and we know that y is equal to f of x, and we know that y is equal to f of x. Now f of x is what? 4x minus 1. It means y is equal to 4x minus 1. From here, after doing some little calculations or algebra, we can take y plus 1 is equal to 4x, and x is basically y plus 1 is equal to y plus 1 divided by 4. So this is x basically. Now whether this x is real or not, because we have to find x, we have to show there exists some x belongs to r, means x must be real number. So whether this y plus 1 divided by 4 is real or not? Yes, of course, y is real, y plus 1 is real, y plus 1 divided by 4 is real. So x is real. So there exists x which is a real number. We have showed the first, we have proved the first condition here. Now the second, does really f sends x to y? Now the function f of x is basically, we substitute x here, x the same here, sorry, what is given here, f of x, we have calculated that x is equal to y plus 1 divided by 4. So in f of x we have substituted the value of x, y plus 1 divided by 4. Now if we apply function on this value, now suppose this is z, if we have f of x equal to 4x minus 1, then f of z is equal to basically 4z is equal to 4z minus 1. If we suppose this is z, then if we apply f on z, then what will happen? 4z minus 1, then 4z minus 1. Now we simplify, 4 is cancelled out with this, and we get y plus 1 minus y. 1 is cancelled out with 1, and we get y. So what we have done here, we have proved that f really send x to y, as we have supposed f of x, f of y plus 1 divided by 4, and we have arrived after some steps at y. So what does it mean, f of x equal to y? It means f really sends x to y. So therefore the given function is the given function f of x is onto function. So this is how we can prove an infinite a function which is defined on infinite sets. We can prove it onto function. Now we take the other function which is given here, h of n 4n minus 1. We apply the same procedure as we have applied on the first example, but here you will see that this function is not onto function. H of n is basically 4n minus 1. We suppose it m, because here we had x and y, f of x equal to y. Here we suppose that m is equal to h of n. Here y plays the role of m. Now m is basically 4n minus 1. Now n is what? This is basically, you can say, m plus 1 divided by 4. Now we have to prove n is equal to m plus 1 divided by 4, and we have to this here, h of n is 4n minus 1. We suppose m is h of n, and we have found here n is basically m plus 1 divided by 4. Now to prove that this function is onto, we have, the first step is that we have to prove that there is, first we suppose for all m belongs to z, we take any arbitrary element m belongs to z, which is from the second set. We have to prove there exists n belongs to z such that f of, sorry, here we have h of n is equal to m. So we find here n by using the definition this. N is what? N is m plus 1 divided by 4. Here m is what? Integer, because m we taken here integer. M plus 1 is integer. Now m plus 1 divided by 4, I doubt this or this number may not be an integer. For example, if we suppose that m is 2, m is 0. If you take m is equal to 2, you can take any other number, but n is equal to what? By using this expression. This is 2 plus 1 divided by 4, which is 3 by 4. Now whether this is an integer, this doesn't belongs to z. Similarly, if we take m is equal to 0, n becomes 1 by 4. Whether this belongs to z? No. So the first condition is violated here, that there exists some n belongs to z such that h of n is equal to m, because there doesn't exist, there may not exist, there may exist, but we are trying to find the counterexample. So here we say that there may not exist some n belongs to z such that this condition is true. So this violates the first condition. So therefore we doubt here that this function is not onto. We doubt. Now we shall try to find some counterexample which confirms our doubt. or you can say that if there is some problem here, you can claim that this function is not onto, and then to prove our claim we shall try to find some counterexample. Here I have given some counterexample which proves that this function is not onto. If the function h from z to z is defined by this, the codomain of h is z and 0 belongs to z, we take in the codomain. But h of n is not equal to 0. Yes, this is a very simple example. H of n, basically h of n, h is function from z to z. Now 0 belongs to z, obviously z is a set of integers. Now here it is possible to take 0 from the z, but h of n is always non-zero. Why? Because whatever you take here, the value from this z, whatever you take, the value of n, when you put it here in this function, we cannot get 0. If you take 0 here, we get -1. If you get 2, if you put 2 here, we get 7. If you put -1, then you get -5. We shall never get 0 in this set. So 0 is an extra, or you can say not utilized element in this set. So therefore this function is not onto. Or we can prove it like this. For if h of n is equal to 0, then we can put h of n is equal to 0 means 4n minus 1 0, which implies 4n is equal to 1 and n is equal to 1 by 4. And 1 by 4, this doesn't belongs to z. This is not an integer. Hence there is no integer for which h of n, not f of n. Here we must have h of n. H of n is equal to 0. Thus f is not onto function. So I hope you understand what is one-to-one and onto functions, and how we can prove any given function, whether it is one-to-one function or onto function. So now we are going to the next topic, which is one-to-one correspondence, or we say that it is a bijection function, or we see that bijection or bijective function. Bijective function, you can say also this bijective function. So what kind of functions are bijective functions, or what is one-to-one correspondence between the sets x and y? A one-to-one correspondence or bijection from set x to a set y is a function f from x to y which is both one-to-one and onto. Means any function which is both one-one and onto. Shortly we usually say it one-one function, or you can write it one-to-one, or you can say it write it one-one like this, or you can say it also one-one function. So any function which is both one-one and onto is called bijective function, or bijection, or one-to-one correspondence between two sets. For example, here one element is only connected to one element related to, and all elements in y have some preimage in x, the definition of onto. So this is basically an arrow diagram of the one-to-one correspondence between two sets. It is not necessary to one-to-one correspondence that first is an element is related to first, second is related to second, third is related to third. It can be like this also. If you take the first element, again the same a, b, 1, 2. The x set is basically a, b, c, d, e. The y set is 1 2 3 4 5. Whether if 1 is related to 4, for example 2 is related to 2, C is related to 5, D is related to 1, and E is related to 3. It can be like this because this under the function. This is a function. One element is related to 1 and all the elements in Y are also related to some element in X. So this function is also 1 to 1. This function is also, this is 1 to 1 and on to. This function is both 1 to 1. Therefore this function is, you can say that, bijective function. On the finite sets, or you can say that there is a 1-to-1 correspondence between the elements of X and elements of Y. So this is what the bijection is. We can discuss it for the finite sets. Similarly, for the infinite sets, we can discuss 1-to-1 correspondence or bijection, as we have discussed for the 1-to-1 and on-to functions. Whether in the previous example we can check whether this function is 1-to-1. We have proved it. We can also verify that this function is, so we have verified it. F is onto, and in the previous example here we have proved that this function is 1-to-1 on R, from R to R. This is an example of infinite function which is a bijective function. You can say here f of x is basically what it was, this 4x minus 1. This function, which is defined from R to कितना हुआ है? वो
1 घंटा 1 मिनट
मिटा रहा हूँ मैं, वो लाइन लग गई थी
सर। वो तकरीबन कितना है? 10 मिनट का है,
बस 2-4 मिनट।
2-4 मिनट बस।
So this function is defined from R to R, and we have shown basically 1-to-1. We have also proved this function is on-to. So this function is a bijective function, or we can say that there is a 1-to-1 correspondence between these two sets. So for today, I think it's enough. We stop it here and we summarize what we have done today. Today we have discussed sum and difference of two functions. We have discussed also the equality of functions. We have discussed 1-to-1 functions for finite and infinite sets, on-to functions for finite and infinite sets. We have discussed the bijection or bijective functions, or we can say 1-to-1 correspondence between the elements of sets. The inverse functions we shall start in the next lecture. Until the next lecture, Allah Hafiz.